Okay, it's my honor to introduce this week's DTM seminar speaker, James Farquhar, who many of you will have seen him give a talk in this room about a month ago in the Geophysical Lab seminar series. So this is not out of keeping. James is a very old friend of our campus. James did his Ph.D. at Alberta and then came to the Geophysical Lab in the late 90s, about the same time I came to DTM as a postdoc. Worked with Doug Rumble for a few years, and then he went to UCSD and did a very productive postdoc with Mark Tiemens in San Diego, after which in about 2001 he moved to Maryland to be a professor in the Geology department at Maryland. He is, as I said, a longtime friend of our campus. He was a longtime co-investigator on our NASA Astrobiology Institute program, and we're very happy to have him. And last time he talked about sulfur isotopes in bacteria, and today he's going to talk about sulfur isotopes in meteorites.
Okay, thank you. In trying to fit, this is the first time I've given this talk, so I'm hoping everything works out as smoothly as I dreamed it would. But what I thought I would do was to give a picture of what the sulfur isotope data tells us, specifically multiple sulfur isotope data tells us about evolution of planetary materials. And the way that I thought I would do that would be by breaking it down into three little stories. I've got a story that deals with sulfur isotopes in Martian meteorites, and I'll explain some of the information that we've been able to extract and other people have been able to extract from sulfur. I also have a part of the story that will deal with iron meteorites and achondrites and some of the directions that we're trying to do. And then there's a final part of the story that deals with primitive meteorites, and you may have seen a talk by Gibran Labidi a while ago. This is largely work that he started, and I'll go through that and hopefully not say anything inconsistent. I don't think so with respect to his work. I'd like to just put this in context. You may wonder, okay, why do we have interest in sulfur and specifically in sulfur isotopes? And the reason we have interest is because it can give us information about processes that occur. And the way that we get that information is through slight chemical and physical variations in the properties of substances and materials that are related to the substitution of different isotopic, different masses of sulfur into substances. The other reason why we're interested is because the chemistry of sulfur is actually quite complex. Sulfur occurs in a variety of different oxidation states. It occurs in a variety of different phases. Over here we have gas phase species. This is a model of sort of an aqueous phase sulfur chemistry. And then here are a variety of solid and then liquid phase species. Many of these species are actually found either in meteorites or observed in molecular clouds, and are thought to be relevant or found on Earth. What this does is this means that sulfur, as an atom, is in many different types of bonding arrangements, and it also undergoes many different types of chemical reactions, both in liquid phase, solid phase, and then also in gas phase. What this does for the isotopes is it gives us two measures that we can use to disentangle process. There are processes that are called mass-dependent processes. They arise because the sulfur isotopic substitutions of 32 for 33 or 33 for 32 changes the mass by 1 atomic mass unit, but 34 for 32 changes it by 2 atomic mass units, and it changes the chemistry slightly and subtly, but in very consistent ways. And so it primarily results from motions, so it results from vibrations, rotations, translations of gas phase molecules. And this notation here, which is one of the notations, this delta notation, is basically the deviation of a 33 to 32 ratio relative to that in the standard. And what this expression here is, this delta 33, or variations in delta 33, is approximately equal to 0.515 delta 34, is just an expression of that mass difference, the mass dependence. Now there's another type of isotope effect that's called mass independent effects, And it arises when other factors enter into the chemistry or the physics of the process. Now this could be if you're dealing with photolysis, the spectrum of UV light, how that convolves with the absorption spectra of the molecules. It could be if you're dealing with excited states in gas phase, coupling between states, determining rates of reactions for different isotopic species. In liquid phase, there can be spin-orbit interactions. And then this is if the radius of the nucleus is different sizes as a result of packing. And this doesn't so much apply to sulfur. It can actually change the size of the bonds and the shapes of the bonds by changing the inner orbital fields, which then propagate out to the outer orbital fields. And these things don't depend on mass, but they're an addition to it, and they produce a deviation from this relationship. So there's this other relationship, capital delta, which is the 33 minus this quantity. And we'll use both of those in this talk. So that's the background. Now what I want to do is I want to go through and say something about these types of effects and these types of effects in these three types of environments.
How rare is 33 relative to 32?
33 is about 0.75%. 32 is about 94%.
Pretty rare.
So it's pretty rare, but it's abundant enough to be able to be measured. So this is a picture of a rat hole from Columbia Hills, just to show that and it's a false color image, to show the presence of sulfur on Mars. And it is an element of interest because it's ubiquitous across the surface, and it's present in a variety of oxidation states. It's also potentially contribute to acidity and to other properties of the material. So we try to understand this. Now the way that I approach it is by looking at meteorites. And there are a group of meteorites that are thought to come from Mars. They are argued on the basis to come from Mars on the basis of dynamical arguments, things falling in towards the sun, in Earth crossing orbits, and then also the gravitational well of Mars, and then probably most importantly the fact that the trapped gases in the Martian meteorites trap gases that look like the gases that are observed on the landers. Now there are a variety of different types of meteorites from Mars. These three are Nachtlights. This is a Shergotite. This one is Nachtla, which fell in 1904. Shergati, I think, is 1865. This is a Pyroxenite. This is a basalt. This is another Nachtlight, Lafayette, which has this beautiful, beautiful structure here coming through the Earth's atmosphere. And then this is a third Nachtlight, MIL 09032, just showing an interesting texture involving magnetite, which is skeletal here, and then small sulfides, which are scattered throughout. There's a potential connection there. And what we're going to do is we're going to look at analyses of these meteorites and see what they tell us about sulfur on Mars and about Mars itself. So this first plot here is from a figure by Heather Franz. This is Heather, this is Sang-Tae Kim, James Doughton. And these are analyses of Shergotites. And what we'll see here is this is a plot of this delta 30, cap delta 33 versus delta 34 with error bars, and that the symbols are colored differently to highlight the fact that these three meteorites that were analyzed were statistically resolvable from a composition that would be 0, which is defined largely by this population. It's actually defined by the standard composition. And so there is an anomaly that's present in some of the Shergotites. It's very small, but it's present, and it's interpreted to reflect the incorporation of surface-derived sulfur into the Shergotites at the time, or in the time when they were either transported or placed at the surface. It presently is as sulfide, and we'll come to an argument that suggests that it probably started as sulfate, so it probably was reduced in the melt. So that's one piece of information that was found from this. The other piece of information is if we look at this cloud of data, there's more scatter in it than we would predict if it actually were a single homogeneous population. It isn't obvious from this plot, but it's pretty close to that. We can get an estimate, making an inference that this is probably the composition or representative of the composition of juvenile sulfur on Mars. And the average for the delta 34S relative to the standard, which is CDT, is minus 0.15, which is very close to 0. This 0.008, which again is very close to 0, and this 0.04, which is again very close to 0. One of these points is the average. The other point is one of the most primitive charagotites, or most depleted charagotites. It's there. So he gives us a constraint on the composition of sulfur on Mars, which is necessary then to take the next step, which will be then to look at sulfur in some of the other Martian meteorites. And so the other Martian meteorites that we talked about, there are other groups, are the Nachtlights. And these are the data from the Nachtlights. This box here would be the limits of that plot shown before. Not the limits of the data, but the limits of that plot. So really, the charagotites just sit right in there. These data points here are sulfides. I'm going to focus on them next. But the key point here is Nachtla, which is a fall. Sulfate was extracted from Nachtla, which is a fall, and it has much larger deviations in this capital delta 33S. So it shows a very clear signal of this anomalous sulfur, which implies that the sulfate in these meteorites was processed through the atmosphere, and that the oxidation reactions that produced the sulfate contained an element that involved this atmospheric processing. It doesn't rule out other hypotheses for the oxidation pathways of sulfate, but it clearly implicates the atmospheric process. These data here, which are also sulfates, are difficult to interpret because the Euro-terrestrial rocks sit on this line. The sulfides form here, and if you had any mixing between terrestrial sulfate and any weathering products, you would end here. So these data, I think the most simple or parsimonious explanation is that they are affected by terrestrial alteration. Now, we talked about the sulfides and the charagotites. I want to talk about the sulfides in the Nachtlights, and these are sulfides. This is Lafayette, Nachtla. These are some MIL paired meteorites where there are sulfides. These are ion probe analyses of the MIL sulfides. There does appear to be a clear relationship between these. It's unclear whether this point is at the origin or whether it extends up, but it is clear that it extends down to a different composition here. So these sulfides in the Nachtlights clearly have a component that came from an atmospheric source. We don't think that we're raining out sulfides onto the surface, so the interpretation is that those sulfides were produced by assimilation or uptake of sulfate that was then reduced by these meteorites and potentially led to their oxidation. It's also interesting to note that the Nachtlights themselves are more oxidized than the charagotites, and the processes that led to their oxidation are processes that people try to understand. So we see that we have this assimilation signal. We think that it's sulfate that's assimilated. There is this difference between the ion probe analyses and the bulk analyses. We take bulk meteorites and dissolve them up. I'm not so worried about that difference, and I'll explain why that is. I think it's possible that it's either different parts of the meteorites or different populations of the meteorites. So we can go through that. And this is one of the MIL pairs. Now, paired meteorites are meteorites that are thought to come from the same meteoroid and broken up on the entrance as they came down towards Earth. These were all collected in the Miller Ranges in Antarctica off the ice, and this 03 was collected in 03. These were collected in 09. They all share some interesting and unique characteristics, and one is that they are cumulates with relatively large pyroxene grains. There are very few olivines, and then they have this skeletal magnetite that is distributed throughout, and this is one of the skeletal magnetites. And then they have large sulfides here. This could actually be this one here, sometimes with cristobalite, and then they can have magnetite associated with them. There are large sulfides. There also are small sulfides that are scattered throughout. The ones that can be analyzed by the ion probe are the large ones, And so the fact, and you would think, and I would think that these would make up most of the abundance of the sulfide, but the difference could be something due to the populations that were measured.
And they're identified as Martian from the inclusions?
These are identified as Martian by association with meteorites that have very clear evidence of coming from Mars on the basis of the dissolved gases that are trapped. They share a common oxygen isotopic composition, and that's what that link is there that links them together. These MIL meteorites also have these largest anomalies. So the question then is there a connection between sulfur and the mineralogy that we see here? And I want to go through a thought experiment and just explain the reasoning and what we're trying to do. And this is work that James Doughton is trying to pursue. The first argument is if you take sulfate and you reduce it to sulfide, you need 8 electrons to run this reaction. And if you put it into a reaction which is proposed for generation of the magnetite, so this would be the iron component in olivine or the iron component in a pyroxene, this would be a calcium sulfate, this would be a jarosite, you will form a small amount of iron sulfide. You'll form more magnetite, and abundance-wise, volume-wise, the magnetite has many more atoms, so it actually fills up a much larger volume. And then you have to put the calcium or the potassium and the silica someplace. Okay? But we can calculate what the volume ratio of troilite, in this case, to magnetite should be. And you get something like 9 to 91, 9% troilite to 91% magnetite out of the two, or 8 to 92, depending on which reaction you're looking at. It's a fairly constant value. As a way to test this, and the preliminary results is James Doughton laid grids over a series of these and counted the intersections with magnetite and pyroxene. Didn't count 330,000 points. Instead, he counted the points of magnetite and pyroxene and looked at the abundances there, which essentially gave him enough statistics to make this determination of the sulfide to magnetite being 5.5. This is about plus or minus 0.5 at the 2 sigma level to 94.5 ratio. And the abundance of magnetite is actually pretty well constrained in these sections at about 1.3%. And that's just based on counting statistics. So to use that information and to reconcile the abundances that are seen with the abundances that are predicted by that reaction, we need to do some additional thought. One is we need to think about if you have a melt that comes up, was in a chamber, and then comes up and is erupted, and then accumulates sulfur, okay, uptake sulfate, you're going to have some initial sulfur in there, and you need to correct for that. And so as a first order correction, we just assume the initial concentration in these melts is probably similar to one that does not have a lot of magnetite knockup, which was about 106 ppm. And that still leaves behind significant excess in troilite in the MIL meteorites because they're sulfur rich. If you count up that, you can account for about 45 or 50% of the observed magnetite just by the troilite that's in the rock. Now, if the troilite was undercounted because it was weathered, and you can see here how it breaks up, then this would be a minimum estimate, so the estimate would be higher, the amount that could be counted. If you have other iron 3+ in the minerals, which is known to exist, this will be a lower estimate. This work is yet to be fully completed, but this is the project that is underway, and I think what we can say pretty clearly is that we do think that there is a link between sulfate uptake and reduction in the melts to formation of the magnetite and the oxidation state of this rock. I think we'd say that pretty conclusively. In addition, the other things that we can say is we do have constraints on the isotopic composition of juvenile sulfur, and we'll come to that in a moment, why that's potentially important. We have evidence that there is photochemical oxidation and atmospheric deposition of sulfur to the surface, so it tells us something about where the chemistry is occurring. And there may be implications. One of the things about these knocklights is they're thought to have come out in a flow. And MIL is the MIL pairs are one of the very quickly cooled flows, cooled parts of one or more flows. And the hypothesis is that either they're sitting at the top of the flow, where it could cool quickly, radiate, heat away, or at the bottom of the flow, where the flow would have had contact with the surface, but not in the middle of the flow, because those would be where the more slowly cooled knotlites would come from. And the fact that these have large crystals is one argument, that they're cumulates, so they might be at the bottom of the flow. And as well, the fact that they have evidence for a fair amount of assimilation at the time of emplacement, that's what I will argue, I would say, is another argument that they probably are at the bottom. So that's the type of information we can get from the...
James?
Yes.
So I think you've shown that there's some mass independent fractionation of oxygen in the atmosphere too.
Yes.
Would you be adding enough oxygen to these rocks to see a difference between the slowly cooled naphlites or the ones that don't seem to have assimilated anything, and the ones that do?
Not from the sulfate. So the abundance of sulfate is modal abundance is something like 0.01%. It's a little bit less than that. And the amount, and oxygen is a major element in the silicate, so you wouldn't expect by the assimilation of sulfate to shift it. The sulfate in knotclot itself does have anomalous oxygen, so it does carry an anomalous atmospheric signal in oxygen in addition to sulfur. The reason you see it in the sulfides or in the sulfur is because it's actually adding a fair amount of sulfur to it, relatively sulfur.
Even if you went to ppm level precision, so you wouldn't see an effect.
Yeah. So you need to divide it per mil by it's by 1/10 of a per mil, 1/10 of a part per thousand. So I think you still would not be able to do it. You'd have to be at sub ppm levels to see it. You could have assimilated other things, and it does. I don't rule out the fact that there could be other oxidants that were brought into this system to drive the oxidation and drive the magnetite. I'm just implicating sulfate oxidation as part of it. Now this is a picture of the South Pole of Vesta, and moves me into the next part of the story, which is another developing area where we're working, where there are some interesting aspects that have come about. Now, I talked about trying to constrain the juvenile composition of sulfur. One of the goals that we have had is in trying to understand what were the compositions of the materials in the inner solar system. And so we have these data on Mars. We also have some data on lunar samples. We'll have some. We've improved our capabilities. We have another project that's going on, or that's soon to start, where we should actually be able to constrain these even better. And then these are Gibran Lavidi's work before he came to Carnegie from Paris, where he studied terrestrial basalts and made estimates on the basis of sulfur isotopic compositions and relationships to strontium and neodymium to project back to what the primitive compositions would be. And basically, for the silicate parts of planets, you find you have a delta 34s. It's negative in both Mars and Earth, slightly positive in the case of the Moon. This is hypothesized to be probably due to devolatilization of sulfur from the Moon, and then silicate metal segregation in the Earth and Mars. Gibran did some work where he suggests that this may be a pressure-related effect related to the conditions of the segregation. The key point here is that everything is very, very close to zero for both capital delta 33 and 36. And where this fit in as well was if you look at iron meteorites, and it's normalized to one troilite from one iron meteorite. This is a troilite grain here in an iron meteorite. The studies of iron meteorites had shown that they had very close to zero or average values. Now this scale is larger. This is a study about 25 years old now, but it did suggest that they had the same composition. Now there was something strange that popped up in the past 15 years, which was iron meteorites, which are either thought to be the cores of asteroids or iron silicate segregations within the asteroids, and then the silicate mantles of the asteroids, which are the achondrites, should be related in some way. And there was a study, I did a study with Mark and Terry Jackson, and then Dina Rai followed up. I looked at Eurolites, they looked at a variety of other meteorites here, and what they found was that for these groups of achondrites, there was a slight enrichment in this capital delta 33 relative to the troilite from one of the iron meteorites. It was the standard. So the question then came up is, was this difference real? Why would the iron meteorites be different than the mantles of the planets that were disrupted, or the asteroids that were disrupted to produce potentially both of them? So we went back and decided to revisit iron meteorites. This is a picture of Grant. This is Mike Antonelli's fingers. This is Mark Peters, who started the project, Mike Antonelli, who finished it, and now is working on a Ph.D. at Berkeley, and then Sang-Tae Kim, who was at McMaster, and he also was working on this project. And I want to quickly go through what Mike found. Now, the key point here is, if you remember the other plot, the whole variability of the iron meteorites was across this whole range, but it's scattered around the origin. These are the same type of grouplet of iron meteorites, the 1AB main group iron meteorites, that the standard that was chosen belongs to Canyon Diablo troilite. And this is capital delta 33 versus delta 34. And what they define, what our analyses define, is a very tight relationship for delta 34s near zero, capital delta 33s near zero, and capital delta 36s near zero. Now, if they come from the same pot of metal and sulfur, and you're standardizing to one of the members, you would expect them to be very close to this value. But they also are very, very close to what we find for the Earth, Moon, and Mars. Okay, so it then, on the basis of these things, you think, okay, what about the other iron meteorites? Now, there are, the 1AB iron meteorites are called non-magmatic iron meteorites, which means they have silicate inclusions in them, and they are thought to be the sort of pods of metal in a differentiating planetesimal that were excavated from that. There also are magmatic iron meteorites, which we'll come to, which are thought to be the cores. So you would have started the segregation of the metal and silicate, and then you would have essentially ended it by moving all of the metal into the cores. And so you've got these non-magmatic here, and you've got the magmatic that we'll come to later. If you look at the non-magmatic, there are arguments that suggest that, and these are several other groups, and they all look pretty similar, that these different groups may have come from different planetesimals, or at least different pots of metal. But there are some of these that are unusual, and we have analyzed some of them, and they are unusual on the basis of their highly siderophile element chemistry, and this is work of Emily Worsham and others. And basically what they find is, if they look at the highly siderophile element abundances of, these would be the SLL group, which I'm going to show up down here somewhere, or no, they're here, and compare them with this SLM group, they find that they're distinct. And they also find that they have different ages for metal silicate segregation. So these things appear to be different and distinct, and they may in fact be resolvable. 2 points is not enough to tell, but given our current level of uncertainty, I think you'll see, I think this potentially could be resolvable. It might not be. We just have to see what happens as we collect more data. We move through, though, we can look at the magmatic iron meteorites, and here's where it gets interesting. The 3Fs, one of these data points is actually from Gowan Thiemens. We have two that we were able to acquire. The 2ABs here, the 1Cs here. This is actually a non-magmatic one that plots near the origin. The 3ABs also plot up here, and then the 4As plot over here. Okay? And there are clear differences that are resolvable in this capital delta 33 between these different groups. It was not seen in the prior study, I think in large part because they didn't have enough samples to see it. I think they had the resolution where they would have been able to see it analytically, but there are differences in the capital delta 33s. Most of them actually have a delta 34s near here. I'll come to that in a moment. But these 4As do show a scatter out this way, which there are puzzling relationships that show up. If you look at indicators of crystallization based upon, say, iridium or gold or something like that, all of these points, not including these two, appear to correlate with the indicators of crystallization. These two don't match up. One of them is a clear silicate-bearing 4A, which is unusual, and the other one is Gibbon. I don't have any explanation for why they should be different than the others, but it is one of the unknowns and some of the features that pop out of this data. I think that this is a chemical signature that is showing up in the delta 34s. I don't know about this point out here, whether that's just a bad measurement or if there's something there. But the 3ABs are another area where we want to look further. But all of these, all the other ones, the average of them is very near zero. And this makes sense if you think about them carrying the bulk sulfur out of the of the planetesimal. So if you undergo metal silicate segregation, the sulfur partitions heavily into the metallic liquid, and then that liquid, then as it crystallizes, it will actually expel the sulfur, leaving behind the sulfides. But it then would pick this up, and this is probably a reasonable measure of the delta 34s of the initial sulfur that we're working. What's puzzling then is why there should be this variability in capital delta 33s. And there's one other relationship. This is something that Mike figured out. At the time that he was doing his work, there was a study that Thomas Croyer and Rich Walker and some of you were doing, studying hafnium tungsten segregation ages. And these are ages that tell you the age at which the metal and silicate would have segregated. And what's striking here is this is the age of CAIs, is that these things had very, very early ages. Basically, you form these planetesimals very early, and then you differentiate them. And the question then is, if we look at some relationship, this is just a measure of the sulfur that was inherited by the planetesimals. It doesn't have anything to do, it would not be processed by the segregation process. But the question is, is this relationship significant? Now, Mike would argue that it is, and he would argue that it tells you something about the materials that came together to form these planetesimals, and maybe then there would be some link to to the heat and the materials themselves and when they would have segregated. But there are interesting features that are falling out of this with respect to being able to measure these things very, very precisely. But the big question then is, what about the achondrites? And the achondrites themselves have some interesting features associated with them. They're one of the groups of achondrites are the eucrites, and the eucrites themselves, recently work by Scott and Greenwood and others, have found that eucrites, which are basaltic meteorites, very, very common, a large number of them thought to come from Vesta, have a very tightly constrained cap delta 17, which indicates they come from a single planetesimal. Yet some of them that look similar, so Ibitira, Asuka, Pasamonte, and this NWA and PCA, clearly look different. Okay, so there are differences in the eucrites. There also are recent arguments on the basis of highly siderophile elements for late addition and re-fertilization of metal into these parent bodies and also into the Earth, and these show up these are diogenites. This is on eucrites here, I believe. They show up in these parent bodies as well. So the question that came up in looking through the data that had been published was whether some of these unusual there's a lot of scatter here for this data, and whether some of these unusual enriched compositions might be a result of some sort of process like that. And none of these are the same samples that were studied there that have been identified. Some of them have not been studied and some need to be studied. So we went back and we decided to go look at these are angrites, the eucrites, the monomictic eucrites, and then also look at pallasites, and we looked at Gujba, which is related to Weatherford and Ben Coven, which are CB chondrites on that prior study, to try to see if we could understand and pick up some of the variability that we see. And this is the data that we have overlain on top of the iron meteorite data. Gujba, basically all of the samples, including the fines, the metal associated, silicate associated, all plot within plus or minus 0.005 per mil of CDT. So we didn't see anything there. We'll go back, we'll look at Ben Coven, we'll look at Weatherford. These are unusual, strange meteorites. It was the fine fractions where they saw something in the Ryan Phelan study. The angrites as well, they define a range of delta 34S. The only thing that I can see, there's no correlation here with indicators of hafnium tungsten or highly siderophile elements on these particular meteorites. We looked at Angra dos Reis, two of the NWA meteorites, and SAH. But there is a variability here that is clearly some sort of fractionation for 34. This could very well be a revolatilization signature, and the question here then is these would be slightly negative in delta 34, which would be interesting. The eucrites plot in a relatively large field, but it's really one point here. It has some unusual textural characteristics, and my understanding is that the group at Open University will analyze it. This is CMS, Cumulus Hills, and then this one here, which is a GRA 98098, which is known to have some sort of alteration associated with it. And then otherwise they define a relatively tight range in here. And then the pallasites define a range in here that actually overlaps with the 380 iron meteorites, which some people have argued there are similarities there. One thing that is clearly different, though, is that the angrites clearly have a different composition than where the 4B analysis is, which people have argued for similar sort of cores being associated with those two groups. So if you look at this, this is from minus 0.4 to 0.4, basically, which would be basically right in here. All of our data for all of them falls on that pink line. And we are resolved here, but we do have some, I think this, let's see, this point here actually just moves right back to here, and this point here moves right up to here. I think that right now what we can say is that some of this scatter is analytical, and it all ends up being, with the exception of a few points out here, within uncertainty, the anomalies still are there and they still are real, but it gives you an idea of where we're going with it. So what have we learned? I think we've learned that these small sulfur anomalies are the rule rather than the exception for these small asteroids. We've learned that different parent bodies have small resolvable anomalies that can be used to evaluate links between the groups. These are not going to be able to be evaluated the same way as oxygen isotopes, but they should be something that there should be a consistency if you want to make those arguments. So it's more a test rather than diagnostic in many cases. And then there's variability in sulfur isotopes, some of which we can link to silicate segregation or to evaporation. And then there is this key unresolved issue, which is what is the origin of the signature, this anomaly? And are we going to find some sort of evidence for mixing from diverse sources? Yes.
So what is the process that gives you the negative delta 34?
So if you have metal silicate segregation, the metal partitions the 34, the heavy sulfur, relative to the silicate. And since the metal partitions most of the sulfur, it can push the silicate to negative values. angrates. And that's the interpretation for the Earth and Mars. That may be the case for those two angrates. Now, evaporation will do the opposite. And so the eukaryote parent body, which, and this is speculation, mind you. Eukaryote parent body is slightly enriched in 34. The moon is slightly enriched in 34. And of those angrates, one of them is a surface angrate. So it's conceivable that that one also could have lost some sulfur. But these are all things that need to be tested. So the next step in this story comes from work that Gibran Labidi and Harry Odoro did. And it builds out of a longer term story that other people have worked on, which has to do with the primitive materials. Now, in these primitive meteorites, you'll find a variety of sulfide minerals, sulfate minerals, or even elemental sulfur or organic sulfur compounds that have been extracted and analyzed. And in analyzing these materials, generally they have been found to be relatively homogeneous. But there have been some exceptions. And I'd like to go through a little bit briefly how sulfur chemistry works, and then show you that earlier work, and then get into our work. So this is a picture of the Orion Nebula. This is the Lyman Low region here. If you look out spectroscopically, and the people here who know a whole lot more about this than I do, people have detected a whole variety of different sulfur molecules in gas phase, from this methyl mercaptan to SO radicals to hydrogen sulfide. There's a trisulfide that's been detected, SiS. And they also detected that they actually carry a different 36S abundance than what's seen in solar system materials. And then, as well, they find that the total amount of sulfur is low. The amount that they count in gas phase is low compared to what they would anticipate should be there. So there's a question about where does that sulfur go? Several things can be said about seeing all of these different compounds, and that's that there's actually a very active chemistry to take things from being mostly hydrogen sulfide to forming all of these other compounds. The radicals as well, and the charged species as well, tell us that there's active chemistry going. The fact that it's depleted is a subject of research where people have been interested in trying to study what happens in ices, and can you condense these things down on the ices, and is that where it is lost? So in these areas, one would expect very rich chemistry, potentially very rich isotopic chemistry. We ultimately come from there. But what we have to go through is the formation of a solar nebula and the formation of planetesimals. And this is where it gets a little bit complex, or probably very complex, in that you have regions where you will be relatively transparent and hot. You may have regions along the surface here where you will be cold, but still impacted by types of radiation and ionizing particles. So you could drive this chemistry to hot chemistry, cold chemistry, and then you have this large area in here where it's opaque, and in the inner parts it gets hot and things get processed, and effectively you remove a large part of what could have been there. But what was interesting, what kept popping up in addition, and that may be the reason why the meteorite sulfur is so homogeneous, what kept popping up came about from some measurements done in the late 70s by Rees and Thode, doing sequential acid extracts on Allende, which is a CV chondrite, and they acidified it, took off sulfur, acidified it, took off sulfur, kept getting stronger and stronger acids. Basically, this is their plot of their data plotted capital delta 33 versus delta 34 from their 77 study, and then the redone 79 study for two pieces of Allende. Largely, they found that the first stuff off plotted down here and was within error of the origin. Their error bars are larger new mass specs and to make more precise measurements. Their chemistry was fantastic. Everything that I've seen indicates that they had done some of the best chemistry that existed. They had two extracts that gave these values of +1, and they had some other extracts in a repeat that came here. And in this case, they did a whole variety of tests to say, these measurements we think are real. At this point, they were looking for nucleosynthetic anomalies, but they could be chemical. After that, Gao and Thiemens came in, and they started measuring a variety of carbonaceous chondrites, ordinary chondrites, and basically they find that in bulk, everything appears consistent with mass fractionation processes. And they refer to these mass independent as nuclear isotopic anomalies. They say they haven't seen those. So they didn't see those. There's some scatter in their data, but they didn't see clear evidence that made them argue that. And the reason why they did that study was to check, follow up on recent codes, so they were aware of it. In addition to this, there was a study by Cooper and others where he extracted sulfonic acids. This is methane sulfonic acid, ethane, propane, this I think is a butane sulfonic acid. And this is a sulfonate group on substitute for hydrogen there. They analyzed both the hydrogen and the sulfur isotopes. The hydrogen isotopes are quite enriched, not super enriched. They're about 500 to 800, 900 per mil. The sulfur isotopes also show anomalies both, and they appear complementary. This is a trace component. The experiment was done once on Murchison. They needed a lot of meteorite. We're trying to set up to be able to do this type of chemistry and to explore this. The hypothesis was that this was a low temperature reaction, not a high temperature reaction that occurred in the colder parts of the nebula or survived from the molecular cloud. So where we did, well, and then there's one more. Rye and Thiemens took Dajala, another meteorite, took chondrules out of Dajala and did the same experiment that Rees and Thode did. And what they found was that they would extract, and they have smaller error bars, they would extract out the sulfur, and then their last extracts, they had, this is much smaller, 10 times smaller than the Rees and Thode anomaly, but resolvable. They had a small anomaly that was here. And they argued that this was some sort of mass-independent reaction. Now, they had a model that was tied to the chondrites. So it's different than the Cooper model, different than a cold origin. And their model, basically, at the time they called on the X-wind, I think basically they were talking about any sort of wind that would excavate things and send them out here. They would have the achondrites being formed from material in the hot region in here where sulfide would be evaporated, and you might be able to get UV light. And then they would have had those chondrules. Their model was that it was injected out and then sent out here. So their idea was that it was all an inner solar system process. Now, when Harry Odoro finished up and Gibran was coming in, Harry went off to St. Andrews to do work. And he decided to, and we were also deciding to look at carbonaceous chondrites. And he requested a piece of Murchison from the British Museum, and we've been analyzing ones from the Smithsonian and I think it's also Chicago at UCSD. And his piece ended up gave an anomalous result, which then prompted Gibran and all of us. He came out, we were all working together trying to reproduce this result, and then trying to work together on the process of characterizing sulfur in these meteorites. And this is work that's underway, in progress, but the first stage of it is largely completed. And what Gibran came up with was a reaction and analytical strategy to extract sulfate, elemental sulfur, and then sulfide. So this would be mostly a sulfide. And there are some extracts here that have not been analyzed yet, but that we'll explore, and extracts down here that this will continue on down. What was interesting, when he extracted all of these and analyzed these for a variety of CM chondrites, so we have sulfate here is this black, or elemental sulfur here is the black, we have sulfate, and then we have sulfides here, was that they show variations in this capital delta 33S, so this mass independent anomaly. The other thing is they're not at the 0.02 per mil level, These are about 10 times larger than that. So they're significant anomalies. And let's see, yeah, so they're significant anomalies. And they're in the bulk sulfur that is extracted. So the first thing is that if we're seeing the variability of CM chondrites, then the achondrites, which we thought were special, were not special. Basically, it was that there were just not enough of them measured. And actually, some of the outliers, MCY, one of the measurements that Mark did is an outlier that sits right about here. And then I think there may be some others in here that also match up. Some of the outliers that were not identified in the Gallen-Thiemann study actually show up here and just fit well with our measurements. So the chondrites are not special, or the achondrites are not special. There is variability both in the sulfate here, which is a water-soluble phase, and the elemental sulfur here, which suggests at least after the formation of this sulfate that there was not a huge amount of water fluxing through these meteorites to remobilize it, pull it out of the system. But there is clear evidence for aqueous alteration. The other thing is, I'm sorry to plot it here, the data from Mark's group from Murchison, which I have no reason to doubt, we've analyzed other pieces, we'll plot down in here, and shows that there is heterogeneity in individual meteorites. Now, we need to go back and sort out with the British Museum what the nature of that material is. I know whether it's a clast or something else, it's unusual, but there's clearly something going on. So the anomaly was not homogenized at a meter scale in the materials that we have. And then I guess the final observation here is that the greatest variability is for elemental sulfur. This is the lowest and the highest. And then the sulfide is in the middle and the sulfate sort of tracks along. This implies, because we think that it's elemental sulfur, that the production mechanism is not oxidation of sulfide, a high temperature mineral, to form elemental sulfur, but that it's something to do with elemental sulfur itself or some precursor. And this is basically where I'll be almost wrapped up. The hypothesis so far, and Gibran had talked a lot more about this, and I can talk much more about it, about different models and ideas about what we think the chemistry is that elemental sulfur as a carrier or elemental sulfur precursor as a carrier would imply low temperatures. And that is because if you want to put it in iron sulfide, you won't stabilize elemental sulfur under those conditions. Elemental sulfur sublimates. So the putting it into these two pools becomes a difficult thing to do. It is a possibility that we had elemental sulfur or a precursor that condensed in ices. The work that has been done both on experimental work meant to model nebular ices as well as molecular cloud ices shows that if you form ices with sulfide, irradiate them, and then sublimate them, they leave behind residues with elemental sulfur and like compounds in them. So it could very well be associated with some sort of low temperature condensation. Where would this anomaly occur? I think it implies UV photochemistry. One thing that Gibran is interested in exploring is whether it could imply something really strange with it being in the ices, but it could also be in gas phase. Probably not the inner part of the disk because that's where it's hot. I would think that the homogenization in the formation, processing of materials before formation of these things probably makes this a difficult suggestion, but that could be wrong. And the preferred hypothesis is that it probably comes from somewhere near the surface of the disk and then is recycled down in. So I think my take-home message is that these are not rare, the anomalies, but they are small, and they're small in comparison to other types of isotopic anomalies in other systems, and I think there's a good reason for that. We're going to continue this work with the primitive meteorites. We'll focus on organics. With the achondrites, we'll focus on trying to look for variability that might put together, be fit with how the materials are put together. And then with the Martian meteorites, we'll continue to explore the potential links between uptake of sulfur and the compositions and the chemistry of the meteorites. So thank you.
Are there questions for James?
James, what do the expected nucleosynthetic anomalies look like in sulfur? Because we know, like in Murchison, for example, both as a whole rock it's got nucleosynthetic anomalies and its individual components.
So nucleosynthetic, you've got someone here who knows a lot more. So I'll tell you what I know and then you get corrected. Nucleosynthetic anomalies in sulfur, as I understand it, can take basically at least 3 different forms. There's a Clayton and Ramadori paper that argued that the production, nucleosynthetic pathways for production of 36S were decoupled from 32, 33, and 34. So one of the things that people were looking for was a 36 anomaly, and that may be the reason why there's apparently a difference between the solar system and these observations in molecular clouds. The other piece of evidence about nucleosynthetic, well, I guess now I got 4. The other information about nucleosynthetic anomalies is that Peter Hoppe did studies of silicon carbide grains with ion probe and finds 32S enrichments in the silicon carbide. And they produce characteristic relationships that are not exactly what we see, but pretty, it would be difficult to differentiate between those 2 possibilities with the 33, 34, and 36 for the achondrites, and I think maybe even the chondrites is pretty close. I don't know whether it's slightly different, but pretty close. There are spallation effects that happen in metal phase of iron meteorites, and we're exploring those, and those have been explored before. And then I guess there are different parts of stars that form different relationships. If you calculate down through a star, you would see this relationship or that relationship. But how you get that up is outside of my expertise. But I know it happens for other systems.
I guess my question just goes down to whether these, going back to the classification of meteorites on the basis of oxygen isotopic composition, which is presumably a photochemical effect, is whether with sulfur you're tracking the same photochemistry that's controlling the oxygen, or you're tracking the nucleosynthetic variation that shows up in heavier elements, chromium, area.
My bias is, so the 33, 34, and 32 of the carbonaceous chondrite data shows 2 relationships come out of that data. So for all but these 2 points, there's a tight relationship between 33, 34, and 36 or 32 that looks like some photolysis experiments that were done with wavelengths at Lyman alpha, in Lyman alpha region, with H2S. For these, you could also photolyze them with longer wavelength regions. There are several different absorption bands for H2S, and these match with longer wavelength H2S absorption regions. So where I would push it would be to say that I think this is photochemical. I think the reactions themselves, the place where the photochemistry is occurring, though may be different than where the oxygen photochemistry is. So I think it's a similar process, but could very well be in a different part of the system.
John?
Going back to the second part of your talk, it seemed like there was an implicit assumption there which may not be correct, which is that the achondrites and the iron should have anything to do with one another. It's entirely possible they form like different mechanisms at different times or at different parts of the cell nebula, so we shouldn't necessarily expect them to be matching up or complementary at some time.
So there is that. I did make that assumption, and I agree that it's difficult to connect them. As far as ages are concerned, some of the irons, the metal silicate segregation ages put them as forming very, very early, and at least the angrites as well formed very early. I think the eucrites form a little bit later. Where they formed, that's another issue. Some connections have been suggested, but other ones clearly, the connections that are suggested are, they say, this one formed in a body with a core with material like this. So the angrite 4B connection, for instance, they're not thought, as far as I understand, they're not thought to be connected, but there are some aspects of their chemistry that are similar, and so people look for processes being similar. They could be in different regions. I agree. I'd be interested in talking more, learning more, because I think you've got it.
While you're on that subject, you said in your talk that there's mass fractionation associated with core formation.
Yes.
Yet I didn't see a huge difference in the isotope delta 34 for the iron meteorites and the achondrites. Can you put
Yes.
a limit on how much core formation they see?
So this is where the, on the basis of sulfur, I can't put a limit on the amount of how much core formation they would have seen. That would be on the basis of other systems, I would assume.
Why not if there's a mass fractionation?
If there is a mass fractionation, I think, so most of the sulfur goes into the metal phase.
Right, so your achondrites
So
should be
the achondrite should pick up something. And there's a problem, because the achondrites that have been measured show 34S enrichments. That shows up in the eucrites, which I showed, but it also shows up in the uralites, I think in the alkylpolcolites. And if you're dealing with metal silicate segregation, you expect a 34S depletion. So, first of all, the achondrites have and I realize I'm going through and it sounds like I'm disproving things that I've said. The achondrites have a small fractionation. It's unclear where that originates from. One possibility is that it's an evaporation. It's lost some other way. The constraints on the fractionation between metal and silicate are largely the constraints that Gibran did in experiments here, and they suggest that the fractionation is variable depending upon the compositions of the melts, and there may be a relationship between composition and pressure that would allow for in some cases for metal level fractionations to be expressed in the silicate fractions, but in other cases not. So Mars itself is only fractionated by a 10th or 15th of per mil if we say that the origin is about 0. So,
I have one question on this graph and then another one. What fraction of the sulfur in CMs is elemental from this analysis? And is it conceivable to find it in situ?
Okay. I'm sorry, that's a number I should know. I don't know. I can find out. Finding it in situ will be difficult because elemental sulfur will evaporate or sublimate in vacuum.
Yeah.
And it's puzzling. Documenting that it's elemental sulfur is not trivial. We can document that this was elemental sulfur in the ethanol extracts that were extracted. The ethanol extractions were done in an anoxic system, so we don't think that we would have produced it in that extraction procedure, but there are reactions that can produce it that way. There are independent extractions of elemental sulfur with other solvents, benzene for instance, that avoid some of those complications but introduce others that tell us that there's elemental sulfur there. But this is identified as elemental sulfur in the ethanol,
Right.
not in situ. And then there's the issue of how then do you bring it in with the meteorite coming in, and the argument there is the meteorite is cold, so it doesn't actually heat up and evaporate away.
Can you show your iron meteorite data again? You had it on. Sorry.
If I knew how to drive this thing, I would be better.
Yeah, something like that.
Okay.
That doesn't-
There. This doesn't actually have all of them, but I can tell you where
I was trying to see scale, but everything is normalized to Troilite and Canyon Diablo.
which is,
and-
yeah, which is
Which
that
is
block.
presumably because there's a ton of Canyon Diablo, it made Meteor Crater in Arizona, and it has sulfides in it, so it's
Yes.
an easy way to get a standard. But looking at this, what if one of these other meteorites had made Meteor Crater and had sulfides and was the standard we all use? Do we just get lucky that the thing that matches the Earth and Mars is the one that made Meteor Crater, and that was what we decided to use as a standard?
I think so. So it was chosen as a standard in the 1950s. And there's several levels to it. Different people have done measurements, and when they first started measuring anomalous compositions in terrestrial samples, one of the hypotheses was, well, maybe Canyon Diablo was anomalous relative to Earth.
Right.
That didn't turn out to be the case. The other aspect of that question is, I don't know where on this plot you would fit the sun,
Yeah, I guess that's really fundamentally what I'm getting at.
yeah, or the rest of the solar system.
But if you chose the average of all of those as the best measure of the average early solar system, I guess it would just shift everything a little on the plots, but not change trends.
It won't.
If you use the
no, we
different
just move it
normalization.
up and down
Yeah,
on
yeah,
this
yeah.
plot. Yeah.
Anyway. Okay, well, if there's no more questions, let's thank James again.
Sorry, I'm on the nine folks, sorry. That's fine, that's fine.
Did you find the mount with the iOS on it? Can you find some iOS?
Just chewing up, we'll just he sent me something about and I said, as far as I was concerned, I didn't need to see it again, as long as you were.
I've got a version 11 of that. I'll I have to read through it. But I did want to chat with you just at some point about his stuff, just so that I understand, because we've got various questions and I don't know a quick answer.
Okay.
He's got,
Is there a spot?
oh, but I don't know them right now. I have to go back and read them. I'll just be following.
I'm meeting with him at 2:30 if you want to join in the conversation. Or we could just come down to the Nannisons and bug you and talk to you.
And then the next thing is, as we continue this, is trying to figure out. So he's got right to, we found all these papers about the bases of chemistry.
It's a whole kind of
Oh, no, it is. He was going to contact the people who do the experiments.
I actually just didn't want to get him too distracted.
He's distracted.
I think that needs to be sent out for review now. I think it seemed like we were just going round and round in circles. It'd be interesting to see what other people think of it. It's very puzzling data, but it's very interesting.
So, but we have that IOM, or he wants us to do HF on it first, and then start working on that, on the organics. And then there's the water cycle. And we just ordered an IC, an ion chloride,
Okay.
that HPLC and an IC, but that's where we'll use that potentially for separation. So maybe we can do sulfonic acids.
Yeah.
Symphonic?
Sulfonic. Symphonic. Hey, Doug.
How are you?
Good.
Nice to see you.
So Henry Claus